We met with Noctua for an in-depth engineering topic, and it featured some technical language. But you could kind of hear a repeating like, woo.
Yeah. Woo, woo. Do something like a quicker woo, woo, woo.
This is Jakob, and he's here today to help explain something.
And the German term for this is Schwebung. Which,
or in other words, the beat frequency of fans. This video will help explain what you're seeing right now, the pulse of the fan blades as they spin, except as it actually materializes in potentially annoying noise. The topic came up when we were discussing the extremely complex subject of fan acoustics, and we needed some help from expert engineers to better understand why we were hearing an annoying noise that sounded like
woo, woo.
Sometimes, and try to keep up with the technical vocabulary. Turns out, it's all about the
Schwebung.
Hey everyone, so I'm joined by Jakob Dellinger from Noctua. Last year we had an awesome discussion about fan engineering, and that was the one where we were getting kicked out of the convention center while we were talking. So today we have some really cool fan engineering topics, and a lot of this kicked off because we recently published a review of, I think it was the Height Y70 case, and on my team's side we noticed a distinct sort of humming noise. And Jakob actually emailed me and said, I think I know what that is. And so that's our topic today. Before that, this video is brought to you by Thermal Grizzly's Aeronaut and Hydronaut thermal pastes. Aeronaut is Thermal Grizzly's entry-level thermal solution, marketed as resistant to curing and for long-term endurance. Hydronaut is Thermal Grizzly's next step up, targeted for overclocking and higher performance applications. We've used Hydronaut on a lot of our systems internally over the years. You can learn more at the link in the description below.
The background phenomenon is an acoustic interaction that can happen when two fans run at almost the same speed. Acoustical term for this is called beat frequencies. In a nutshell, the physics behind it is that when you have two signals that are very close to each other in frequency, you will have them shift in and out of phase slowly. So you will end up with a sum of the two signals that is strongly modulated. Like when you have full constructive interference between the two original signals, you will have a high amplitude on the resulting signal. And when you have destructive interference on the two original signals, you will have a very low amplitude on the resulting signal.
The noise in the Y70, maybe we'll drop it in, but that noise, it was almost like, it was almost not noticeable, but you could kind of hear a repeating like, ooh,
yeah,
that type of thing.
That's exactly what it is. The theoretical background is that the frequency of the resulting signal is the difference of the two original signals. So what we've plotted here, just for illustration, is a 9 Hz and a 10 Hz signal. So the resulting beat frequency will be 1 Hz. So this typical slow woo, woo,
right,
woo kind of thing.
For humans, I guess obviously it's very subjective, but generally speaking, I mean, is there a less or a more annoying version of that? You know, like what would be the ideal way to try and fix that or obscure that type of noise?
So basically, the faster the difference, the bigger the difference in frequency between the two original signals becomes, the faster the beat frequency becomes. And the faster the beat frequency, the less obvious it will be to human hearing. So you will go from a slow woo, woo to something like a quicker woo, woo, woo,
right,
until it eventually blends into background noise. Not any type of resonance you get is due to beat frequencies. There can be various other reasons for resonance phenomena, like just one component putting out vibrations and that hitting the natural frequency of some other component, and that makes your panel vibrate or something like that. But beat frequencies do occur when two fans run at almost exactly the same speed, and that is much more likely to occur when you have fans with extremely tight speed control.
Okay.
So you've been using our NF-A14 fans, our current generation. where you've actually been a bit unlucky to run into this phenomenon, because usually you see like a little bit of fluctuation in speed with each fan running, and a little bit of variation from sample to sample as well. So the risk of them being so close in frequency that you get this woo 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 kind of noise is actually pretty low. But with the G2 fans we're preparing, and we're going to show here at Computex this year, we are actually using a new fan driver IC, NF-A14 that enables us to do much tighter speed control, and a feature we call super torque. We basically give those fans extra torque headroom that they can leverage when they run against working against back pressure.
Okay.
So most normal fans drop a little bit in speed when they work against resistance, but with the super torque feature we can have them keep the same speed, so they push more air through your radiator or heatsink. The downside of this super tight speed control is that you're more likely to run into this type of beat frequency phenomena.
Because they're more likely to align on the same...
Exactly. Usually
RPM.
we have something like a 10 RPM tolerance between these fans, and that's exactly when you run into this type of phenomenon.
Okay. 10 RPM tolerance is pretty tight tolerance, so...
that's the typical range we're seeing, and that's why this new G2 fans prompted us into going for a technical solution for this issue. And the way to go for this is that you introduce a speed offset between the fans. The bigger the difference between the two original frequencies, the faster the beat frequency becomes. So in this case we've shown 9 Hz and 10 Hz signal and the resulting 1 Hz beat frequency. And if you go to the next slide, we can see that this is a 6 and a 16 Hz signal for illustration, and you can see how the resulting beat frequency is just much faster, but also you don't have that huge magnitude between the individual spikes. Yeah, this is actually, now we're going into fans, because for the first illustrations we used like super low frequencies because it's just easier on the charts, and now we're going into explaining what actually happens with a fan. So to see what happens with a fan, you first need to check or understand what the main frequency component of a fan's noise output is, and that is the so-called blade passing frequency. You can calculate that by taking the number of blades, multiplying it with the RPM speed, and dividing it by 60, because RPM is in minutes and Hertz for frequencies in seconds. So in this case, we assumed that we have 2 of the regular PWM models and the 10 RPM difference, like the typical maximum variation we see. So one is running 1505 and the other one is at 1495. And this way we can see that the resulting beat frequencies are 225.75 and 224.25. And we can already see when we overlay the two signals how slow they shift in and out of phase. And this is what gives that slow kind of humming interaction. We go into psychoacoustic territory when it comes to the exact point where the beat frequency is no longer noticeable for users. But it's definitely the faster the better. But when exactly you cannot hear it anymore at all will really depend on your individual hearing. Some people are more sensitive to fast beat frequencies than others.
Okay. You wanted the next one, I think?
Yeah, exactly. So this shows what happens with the offset fans. We call them PPA and PPB, the two fans for push-pull A, push-pull B. The PPB model is running at 1525 and the PPA is running at 1475. So we have a roughly exactly 7.5 Hertz difference between the two blade passing frequencies. And you can already see on the overlay how much faster they are shifting in and out of phase. You can already see points of like complete destructive interference and points of complete constructive interference. The next graphs are going to show exactly what happens if you look at the resulting beat frequencies. This is the slow one without offset. Next one is the much faster one. And I think we have another slide where we have them on top of each other, where it's immediately visible that you have this slow woo 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 without the offset and a much faster without. As I've already said, the bigger the offset, the better from an acoustical perspective, but sadly for our acoustic engineers, we cannot only look at acoustics, we also need to keep cooling performance in mind. So we cannot just create a huge offset to make these phenomena go away altogether. And that is also why we opted for pushing one fan slightly faster and pulling the other one down a little bit, so that we actually end up with the same thermal performance, but much improved acoustics.
So I think I have the answer to this, but just to clarify for everyone, is there an instance in a practical sense where a single fan ever runs into this type of humming problem from the beat frequencies as opposed to just other case vibrations? Does it always require basically two fans?
Yeah, I couldn't think of a situation where a single fan would produce a similar phenomenon. As I've said before, resonances and vibrations can happen due to all types of things.
Right.
So if you see that kind of humming with a single fan, it's not beat frequency, because beat frequency is always interaction between two signals.
So I think it's a good opportunity. I'll throw this out there. If you're not prepared to answer, that's fine. But we've in the past talked about panel design, perforations in cases. And it is a different type of noise, I guess, or vibration. But one of the things that's come up is this concept of longer slats in a panel versus holes. Yeah. And just as an example, the fractal Terra, we observed when the fan was close to those slats, it made a really, I guess, undesirable noise. And then we pull that panel off and we just kind of hold the normal mesh panel to it, went away. Yeah. So off the top of your head, I mean, could you walk me through again why that happens?
Sure, absolutely. As a preface, I should say that intake acoustics are a very challenging field in general. So fans much prefer pushing through something than pulling through something acoustically. But you can definitely go a long way improving an intake grill design for better acoustics and better flow rate. I would also say, before I go to answering your question, that just the fact that it was quieter holding a different panel to it doesn't give you the full story unless you measure how much flow went through.
Right.
Because, for example, when you have a grill that creates nasty acoustics, you could fix that by putting a finely grained mesh between the grill and the fan. It will, in 99% of the cases, it will sound much better. But you're cutting flow by, I don't know, maybe a third or something like that. Yeah. So maybe that's not worth it. Yeah. But now when it comes to like grill design or panel design as such, the problem with those long slits is that you create aerodynamic situations with big pressure differences. And the big pressure differences are creating noise. Not only noise, they also create turbulence that can be detrimental to airflow, but they create a lot of noise. And the problem is mainly that you get situations where the fan blades are relatively parallel to the structure. So you have a situation where the pressure gets extremely high, it drops, and then it builds up again. And this fluctuation between high pressure and low pressure is what creates these nasty high-pitched intake noises. Okay. And by contrast, if you have a panel with like just circular punched holes, you will have the interactions broken down to a much more microscopic level, because you don't have that big structures interacting, but actually a lot of like individually different aerodynamical situations at each point of the blade or at each hole where the blade just passes. And that means that the resulting noise is spread out over a much larger frequency spectrum than if it just passes a single strut.
That makes sense.
And this, like passing a single strut, will create a typical high frequency spike that you then perceive as this annoying intake or a suction noise.
Right. Yeah, no, that makes sense. And
but there's a relatively straightforward solution to it if you have this kind of panel and if you have the space. If you give the fan a little bit extra breathing space, something like 5 millimeters often enough, 10 is great if you have the space. Then just you can 3D print a spacer, or we sell ones for our 120 and 140 millimeter fans. And if you offset the fan from the panel by 5 millimeter or 10 millimeter, you will have much less of these pressure fluctuations, and it can significantly improve both acoustics and performance.
Yeah, it gives it more space. I mean, yeah, we've seen that with, just as an example, but one of the cases we worked on previously was side intake. If you mounted the fan on the outside of the rails, still inside the case, but versus inside the rails, it's about a 25 millimeter difference
Yeah.
or so.
Yeah.
And the noise difference, of course, is massive.
Absolutely.
So,
Yeah.
that makes sense. How about back to this stuff? So what was your next thing?
Yeah, this is now actually going from the theoretical side. The graphs we've shown before were simulated isolations of the fan's blade passing frequency. And these are spectrograms made from real recordings, so they are much more complex and not as simple on the paper.
Let's break down the chart first for people. So if I remember correctly, this is one of the ones that would normally be a 3D.
Yeah, it's actually
3D
a
chart.
3D chart collapsed into 2D, so it's a little bit easier to view. The different colors are basically just lower frequencies that are further in front. But the key point we want to get across with this is that you can actually see difference between the very slow and high amplitude beat frequency that occurs without a speed offset, that's on the left, and the much faster modulation and lower peak to valley difference that we see once we introduce the speed offset.
So not just modulation, but also the amplitude is part of the story.
Yeah, it's both the speed and the amplitude that are so important for human hearing, because it's the volume differences that you register, but also the faster it becomes, the less noticeable it becomes.
And then the 3D chart, just for people who haven't seen them, can you explain what those typically look like? Like, what are the axes?
Yeah, like it's now we have like SPL sound pressure level on the y-axis, time is on x, and Z that we have collapsed here would be the frequencies.
Okay, got it.
But in this case, our main focus is on the blade passing frequencies. That's why, for simplicity's sake, we have collapsed it into 2D.
Should I go to the next one?
Yeah, sure. So yeah, this is actually brings up an important point, because the issue with those beat frequency type phenomena is that they are not just acoustically relevant, like in the sense of what you can hear and perceive, but they can also have an impact on vibration. So it's actually relatively easy to imagine, and we will demonstrate that visually with the samples we have here, that when you have that slow type of periodic humming, it can build up into a vibration that can then transfer through
rattle
the system.
something maybe.
Yeah, if that is relevant in your particular system is hard to tell. Some rigs are more prone to vibration than others. It will depend on your case panels. It will depend on like how you fix the motherboard to the motherboard tray, CPU cooler mounting. So lots of factors.
Anything that's loose.
It's not like everything would vibrate like hell if you don't have the offset. But by introducing the offset, we can just make sure that it's not going to happen.
Okay.
So when we look at the charts, it's again time on X, and then we can see the intensity of the vibrations. This was recorded with a contact microphone installed like on the base of the cooler.
Okay.
We can see those like darker dots at around 300 hertz range. And you can see that they persist for a relatively long time and then drop off and then come again. And if you compare that to the offset, you can see that it's so fast paced, and low intensity, that there's just no risk of vibrations building up.
Yeah, because I guess ultimately we're looking at these, I mean, on the screen in front of us, that's, I apologize, a half an inch. I'm going to use imperial. I apologize for the blasphemous imperial, but a much larger block here. So is that representative of the vibration you're talking about?
Yeah, that would be exactly this building up and then going again.
Okay. And then
generally, the slower you have some pressure fluctuations that can be audible as noise, but can also result in vibration. The slower you have them build up and go again, the higher the risk of like resonance build up and transfer is.
Right. Okay.
In German, we have I don't know if there's an equally fitting English term. In German, we say Aufschaukeln of vibrations. Like Schaukel is a swing, like kids playing on a swing, right?
Right.
And the vibrations, if they aufschaukeln, they go like.
Okay.
And this like really is a good picture for them getting more and more, right?
Right. Yeah. It's almost like a pendulum type of thing.
Yeah. Totally.
Yeah. For this chart, so just to put some products to it, I see you have marked the NF-A14, actually in both places. So what are the two hardware configurations here?
It's the same coolers as we see standing here. So our existing U14S coolers with the new NF-A14 X25 R, so the round version fans installed to it. Upper graph is with the regular standard 1500 RPM PWM model, and the lower one is with the PPA, PPB model, like that's the name. Names we use for the offset kit that comes with one fan called PPA, one PPB, so that you can figure out which one is which.
Okay, cool.
As a rule of thumb, you want to have the faster fan running in front.
Okay.
But this is also something that can depend on individual hearing preferences. So users will be very welcome to experiment which configuration they like. This brings us to another important point to mention, and that's the fact that, as we've already discussed, generally the faster the beat frequency, the better. And the exact point where you will no longer be able to perceive it will depend on psychoacoustic preferences. Okay. When we decided for that 50 RPM offset, plus 25 on the one fan, minus 25 on the other, we basically went for a point that we saw fitting for most users to be no longer noticeable, or at least not distracting, without sacrificing thermal performance. But if you are more sensitive to faster beat frequencies, you can easily just slow down the second fan a little bit further to make the sound signature even smoother. And that's what we can see on the lower bar graphs if you scroll down a bit. These are the two ones we've already looked at before, and those are with even higher speed reduction, so even higher speed offset between the fans. This is with the PPA fan running at 1400 RPM. So basically we're dropping another 75 RPM. At that point, I would say it's really sounding super smooth. So I would be surprised if someone would still pick up the beat frequency there. This is if going even slower to using one of our low noise adapters on the PPA fan, so that's around 1250 RPM on the PPA fan. At that point, it gets even smoother, but at that point you also have the influence of one fan just running slower, which also makes it quieter, of course. And at that point, depending on your application, you may also start seeing slight performance impacts, of course.
If someone thinks that they have this type of noise phenomenon happening right now, happening in their system, and it bothers them, would the general guidance be basically go adjust one of the fan speeds?
Totally.
And then see if it goes away?
Drop one fan by try 50 first, then drop it by 100 maybe. And in most configurations, it's not going to have any drastic impact on performance.
And then if it doesn't go away at that point, it might be a different type of noise.
Yes, totally. I mean, drop it by 200 to be extra safe, but if it's still there, then it's definitely not a beat frequency thing.
Okay.
Yeah, so basically this video is going to show what happens if you have two fans running at almost the same speed. So again, we assume that we have a 10 RPM difference between the fans. I think nicely conveys the acoustic impact you get, this humming type phenomenon. Yeah, let's roll it.
Okay, so we'll drop it in. All right, so that was that clip. That kind of explains that. And then can you set this one up for me?
Yeah, like the next video is gonna show what happens if we gradually increase the speed offset between the fans. So the nice thing about the video is that it enables us not to just show the static situation in graphs, but actually see the acoustic transformation and make it perceptible for customers. So that's what we did here. You can see the two fans, one being increased in speed from 1500 to 1525, and the other one being slowed down from 1500 to 1475, so that we end up with a 7.5 hertz beat frequency that's already much more easy to blend into the background noise. One thing to keep in mind in general with the videos, maybe you were shocked by the first one, how horrible this sounds. How can Noctua sell this? I have to stress that these are based
synthesized, right?
Yeah, exactly. So it's artificially created isolations of the fan's blade passing frequency. And you need to keep in mind that the acoustic profile of a fan is just much more complex than the the blade passing frequency only. So
you strip in all the other noise that would kind of bury some of it.
Absolutely.
Yeah.
So we already briefly listened to the heat sinks before. You picked it up. You obviously have good hearing, but it's not that it's super distracting or extremely obvious.
Right.
So I think it's important to keep in mind, especially when watching those illustration videos, that we're working on a level of, I would say, really acoustic fine-tuning here, and it's not like we have a dangerous problem to fix that would upset the majority of users.
Right.
But we're targeting those who are acoustically demanding, and I think for them the extra optimization definitely makes sense.
Yeah.
We have prepared one last video that shows you what we already discussed with the last graph we looked at, namely what happens if you further increase the speed offset by further slowing down the PPA fan. So in this case we're slowing it all the way down to 1405 RPM, which is I think a level where it should really sound extremely smooth even to people who are more sensitive to fast beat frequencies.
We'll play that one too.
Yeah, so when you watch the videos and when you hear the sounds, you can really hear this ooh, and we have a German term that I think is much more fitting than beat frequency.
Okay.
So when we first started to look into this, and our acoustic engineers told me we have a beat frequency issue, and I was like, what is that?
Yeah.
And then I tried to listen for it, and then I thought, okay, well, what does that have to do with the beat? It didn't make sense to me.
Right.
And the German term for this is Schwebung, which would translate into something like floating or hovering.
Okay.
And I think that really is a much more fitting description.
Hovering makes a lot of sense.
Yeah, exactly.
Yeah, because that's kind of exactly what I would think of for like a hover noise.
Yeah.
Okay.
Exactly.
So then if beat frequency has been confusing,
try Schwebung instead.
Yes.
It makes so much more sense.
Yeah, right. The new Noctua Schwebung, anti-Schwebung fans.
Absolutely. We didn't want to bother you with the German term in the product descriptions, but I think for the Gamers Nexus audience, it should be okay.
It's a special edition. So on this topic, I mean, is there any other discussion you want to go through, or?
I think what we could still show is the live demo on the cooler, because it nicely visualizes what we've just talked about.
Yeah, so you've got some cables here.
I've got some cables. I've got our fan hub.
And then we have some footage of this too we can drop in. So what's going on with the demo?
Yeah, the interesting thing about beat frequency phenomena is that they actually can not only be heard but also seen. So when you have a cooler with those ultra tight speed controlled fans, and the fans running at almost the exact same speed, and you look straight through and have a bright surface behind the cooler, you will actually see this build up,
right?
the Schwebung building up and going down, and I think the fact that how you can see it and how it actually looks when you look at it makes it much easier to understand how this can translate into a vibration phenomenon as well.
It almost looks like it sounds in a way.
Exactly.
Yeah.
I mean, it's not like you can immediately feel it on the cooler that it would vibrate. But it's definitely something that could happen depending on how you set it up. And if we compare that to the unit with the speed offset, you can see how much faster this interaction goes, just like we discussed based on the graphs. And due to the fast modulation of the beat frequency, there's just no risk of that vibration build up that we've been talking about.
Right. Yeah. So this one, if I remember your orientation correctly, here would be the slower of them, where it does that slower pulse.
Yeah. Exactly.
Yeah, and then this is the woo 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 woo. That's
Yeah.
at a higher pace. Yeah.
Yeah.
Okay. Cool. So, in terms of, I think this is all excellent explainer for things, and then we've got one piece of practical advice we already gave, which was if you happen to think you have this type of noise at home, now at least you understand it and you know a couple things you can try, and if it's not from the Schwebung problem, then I'm sure we'll have more topics on acoustics in the future as well. So
Absolutely.
anything else you wanted to cover on this one?
No, I think basically we've covered a lot of ground.
Excellent. And we should have a video live already, probably on the booth. So that'll talk about products and whatever else Noctua has there. We're filming this before that, so I actually don't even know what's going to be there yet. So it'll be a surprise for me as well. And check that out if you haven't seen it. And Jacob, thank you very much.
It's been my pleasure. Thank you very much for having me.
And we'll see you all next time.